All right, let's get started. I'm happy to introduce our speaker today, Professor David McAllester. So if you wanted the academic pedigree, it goes something like, yes, he got his PhD from MIT, he was in the faculty of Cornell. Did you also teach at MIT for some time? Yes, but then Bell Labs. But for the last 10 years, he's been at the Toyota Technological Institute in Chicago. And maybe he'll tell us more about it, but if he doesn't, let me just give you a one-line description. It's a small private school funded by the Toyota Foundation, and it's a great place. And he is the sort of the research head of that. I think his title is something like Chief Academic Officer, but he's mainly well known for his great work in AI planning, learning, and so on. His early papers on nonlinear planning have been quite influential. More recently, his team has done some really nice work on object recognition. But my real reason for inviting him was actually a recent talk he gave at EMNLP. And I thought he had a nice way of telling us how to combine sort of top-down knowledge in all these pattern recognition systems that we use, where a lot of the signal is mainly driven bottom-up. So hopefully he'll touch on some of these things today, because the title of his talk is very suggestive about learning object detection grammar. So thanks so much.
I apologize for the title slide. The last time I gave this talk was to a bunch of undergrads at the University of Illinois, and I was trying to push TTI Chicago. The technical content of this talk is joint work with Pedro Felsenswab and Ross Gershik. Okay, the first part of this talk is going to be somewhat philosophical. At the University of Chicago and at TTI, we've had some interaction with the statistics department. And a classical question, or a current question in machine learning, is what's the relationship between statistics, which is an old field, lots of built-up knowledge, and machine learning. And I used to think that machine learning and statistics were converging, that eventually statistics and machine learning would be the same field. I don't believe that anymore, or I think it's going to take a long time if it does happen. And I think the reason I don't believe that is this list of problems, which for me sort of defines machine learning. Machine learning, I think, it feels to me, is defined by a certain class of sort of paradigmatic problems that it's trying to solve. So vision, computer vision, speech recognition, natural language translation, information retrieval, natural language question answering, ad placement. A lot of these are things that are done by Google. Recommender systems. Protein folding is an interesting one. It turns out Jinbo Zhu at TTI does protein folding. If you know what that is, it's really a problem in computational chemistry. Given a protein sequence, how does it fold? It's somewhat surprising, but graphical model inference methods and machine learning methods turn out to be very important in that application. Genome annotation. So the idea is that there are real engineering problems that sort of define what we're trying to do, or what I would like to think the machine learning people are trying to do. And these problems, I don't think statistics departments are ready to be engineering departments. A lot of what you have to do for this is sort of be, at least to some part, be an engineer. One of the things that's surprising, and one of the things that makes machine learning an exciting area, is sort of the orthogonality of these research areas and the methods that machine learning people bring to bear on them. So the idea is that there's a set of general purpose machine learning ideas and methods that you apply across all of the areas on that previous list. So something as simple as a support vector machine, and support vector machines in the last 10 years have undergone considerable evolution. I'll be talking about some of that later. How many people have seen a support vector machine? Oh my God. The last time I gave this talk was to a bunch of undergraduates at the University of Illinois.
So while we're making trouble for you.
Okay.
You had the Netflix prize up there. And the
Did I?
Netflix prize was won by the statistics department at Bell Labs. And they really consider themselves statisticians, not machine learning.
Okay, my experience is with the University of Chicago Statistics Department. And they are not very happy with the Netflix people. So these are all standard sort of toolkits that get applied across all these domains. There's a little story I like to tell. Back in the 70s, and this may be a little controversial, the stock Fox community, theoretical computer science, was doing lots of things that actually made a big difference across a broad domain of computer science engineering, searching and sorting algorithms, standard data structure work. The stock Fox community has become more mathematical and theoretical over the years, still doing very deep, interesting work. But the idea is that machine learning is starting to play a role in computer science that algorithms used to play. Ideas coming out of machine learning are getting applied across a broad range of applications, and it's become sort of the theory of machine learning and theoretical machine learning and general tools in machine learning are starting to underlie much of computer science. So this is related to this tension I like to talk about between insight and learning. So the statistical revolution probably took place first in speech. So AI in the old days was into rule-based systems. There's Chomsky in linguistics, which is all about grammaticality as a hard notion. A sentence is either grammatical or not grammatical. And then there's been this statistical revolution. And the statistical revolution has been painful in communities in the sense that not everyone easily makes the transition from formal models, like formal grammar models, to statistical models. And in this transition, I'm going to be talking about computer vision, and the transition's been a little hard in computer vision. But there's this famous quote, which I'm sure everyone here knows, which is Fred Jelinek, every time I fire a linguist, my recognition rate goes up. And this was part of the statistical revolution in speech. One thing about statistical models is they're superficial, or at least people complain about them because they're superficial, right? N-gram, trigram language models were much more superficial than Chomsky in linguistics. Another quote I like is from Fernando Pereira. I worked with Fernando at Bell Labs in the late 90s, and he would say, the older I get, the further down the Chomsky hierarchy I go, meaning the simpler the models get. So then more recently, 2010, at a Snowbird workshop, I was talking to Fernando and pointing out that I was going to use this quote in my talk, and he said, oh, those days are over. So at Google, they're trying to climb back up the Chomsky hierarchy and use statistical context-free grammars. So this is another slide just sort of on the same theme. So insight versus learning. So one can argue with some force that a pure machine learning approach makes it possible not to have to understand your domain. So face detection, if you have a digital camera, it has a face detector in it. That face detector is based on an algorithm developed in the 90s by Paul Viola and Tom Jones. And that algorithm, basically, I'm going to characterize it a little bit, but boosting, the third item here, is a standard general purpose machine learning tool. They took the boosting algorithm, modified it a little bit, but nothing really that had anything to do with faces. They took very simple features, built a face detection algorithm simply by running the boosting learning algorithm over HAR wavelets, sort of edge wavelets, and produced a very effective, very fast face detector. But the people who've been working for years on sophisticated models of faces weren't necessarily happy about just turning it over to learning. So in some sense, you could argue that this is undermining our attempt to understand the domains. But another view, which I would this tension between insight and learning, I like to characterize as a tension between Chomsky and Hinton. So Noam Chomsky was very much into understanding language in the domain. Hinton is very much into understanding learning. He's a neural net person. So the flip side of this is that we try to understand learning qua learning, and that the science is in the science of learning, and that there's a lot of insight to be gained in the science of learning. So that's the second view. the new era, those days are over, is to try to unify these two. So what I'm going to be talking about in this talk in the context of vision, so now we're going to switch a little bit and start talking about vision, is the attempt to integrate machine learning with more sophisticated models. So this is going back to the Fernando Pereira second statement that the days in which the statistical models are necessarily superficial and shallow, maybe that's over. Maybe we can get away from that and build statistical models that are less shallow and less superficial. And that includes in machine translation, people are now trying to use grammar models. So what I'm going to be talking about now for the rest of this talk is the attempt to use grammar models in computer vision. So this is a simple, very shallow grammar model of a person detector. So what's going on here is we're looking at 3 different models of images of people. And these models have edges, are based on edge detectors, and you're sort of seeing the edges that the model is looking for. And we have 3 different models. So to detect a person, we're going to take sort of an OR over these 3 models. Each model has these little smaller boxes we call parts. Each part this is a deformable model. In a detection, this part is allowed to move. So it doesn't have to be at the place that's shown in this image. So it's a deformable part model. So there's another level of OR. So you're ANDing over all the parts, and then you're ORing over the position of the part to find a detection. So it's sort of a 3-level alternation of ANDs and ORs. So we were doing this in the context of the Pascal Object Detection Challenge. So I want to talk a little bit about the Pascal Object Detection Challenge. So in the Pascal Object Detection Challenge, we have tens of thousands of images taken off the web. These are just people's photographs. And in these photographs, someone has gone through and put bounding boxes around all of the instances of 20 different kinds of objects. So we have people, cars, bicycles, sheep, bottles, chairs, 20 different kinds of objects, and bounding boxes are drawn around all the instances of all of these objects. And these are the kind of images you get. And you can see they're some pretty challenging poses of people. And they're just images off the web. So the way this competition works, let me first explain the way the competition works, is you build a detector, a person detector. The person detector is going to look at a new image. It's going to the detector will draw bounding boxes, or detections, draw bounding boxes where it thinks there is, say, a person. And I'm going to be talking mostly about person. Its detections will have a score. You sort the detections by score from strongest to weakest. So these are the strongest detections, and it's getting weaker as you go down this. And this number is the recall. The recall is the percentage of actual people that have been found. Okay, so is there a laser pointer here? Comes out of the right side of the podium. Thanks. Okay, so the detections are getting weaker. This is measured in recall. So here, you're getting 20, at this point in the list, you've got 20% of the actual people. So this 0.2 means that's a point in the list where 20% of the people are now on the list. This is precision. This is what fraction of the list up to this point were actually people. So this is 2006. This is the year before we got involved. This is the Dalal-Triggs person detector. You just sweep this over the image looking for places where it responds to the edges in the image. At 20% precision, it's getting 30% recall. So in some sense, this is really terrible, right? By the time you've found 1 in 5 people, 2/3 of your detections are false positives. We got involved the next year. The way we developed our detector was in some sense a complete cheat, but I think it's what people have to do, sort of. We took this detector, which was the winner in 2006, did an exact replication. replicated it, and the publications were great. We could replicate it exactly. We could replicate the results. And then we started to play. Right? I call it graduate student descent. Right? The graduate student tries something, and if it works, you keep it. If it doesn't, you back out. This is our first entry. So now at 20% recall, we're at 45% precision. So this was a pretty big improvement. The big innovation was to introduce these parts. So in addition, we still have that overall filter, which looked a lot like this still. But now we have these parts. This is the most important part, the head. And these parts are deformable. Each part has a nominal position with respect to the root, but it can move, and there's a quadratic deformation cost. So as you move it, you pay quadratically a penalty. And then you look for a best scoring match of the filter, including the deformed parts, to a place in the image. Okay, 45% precision at 20% recall. 2008. This is our model in 2008. Now we have two kinds of people. So we've split the model into two components, two models. We now have two models, each of which have parts. This split into two models and a little engineering tweaks, but this is the big difference. Produced another boost, a big boost, 80% precision at 20% recall. The curve is also looking a lot nicer. 2008. This year we tied for first place overall. I'll talk about that in a minute. 2009 we have three components. Another difference is that these components, these components were left-right symmetric. So this one down here looks weird, right? It looks like twins or something. And that's because these parts are forced to be left-right symmetric. So you have these parts coming in pairs. And that's motivated by the idea that images should have, the statistics of images should have a mirror image of an image having the same probability as so there should be a symmetry in the detector. These models are left-right asymmetric. You can see that this shoulder is much more dominant than that shoulder. They sort of seem to be facing at an angle. But the models then get matched both ways. So you match the left version and the right version. So this is actually a much bigger model.
It's more like 6 models.
It's more like, Pedro likes to think of it as 6 models. I like to think of it as 3 models. But, right. Okay, so this is a table I used to like. I don't like it anymore because now I know what 2011 says. These bold numbers, so these numbers are average precision. The way this is scored, evaluated, is you take one of these precision recall curves and you take the area under the curve, the average over all levels of recall of the precision. And that's called the average precision. And so these are average precisions in different categories. These are sort of traffic scene categories. In 2007, so this is the 20 class average precision over on this column. And in 2007, so bold means it's the winner in that category. In 2007, we were the only ones that did all 20, so the bold doesn't mean much. But what you can see is sort of significant improvement over time. This was our score in 2011, average. This was the winning score in 2011. So the point I want to make here is that it seems, looking at these scores, that there is significant annual improvement. And one thing that's happening across many domains is that we're introducing meaningful quantitative evaluations. And everyone likes to complain about quantitative evaluations, and the metric's never perfect. But once you have a quantitative evaluation and you can do graduate student descent on it, it seems you can sort of get these improvements. So I would like to toss out the idea that maybe there's a new Moore's law in AI performance, that we will continue to get significant improvements every year. And if there's a Moore's law in AI performance, maybe we're going to get there. 2011, I don't have it on the slide, but this number is 41. And we've been busy. We entered the same system again, which was 33.8 this year, essentially the same score. So we're behind now. But 41 is again a significant advance. That was done by a large group from a national research lab in China.
Are the training and test sets fixed across the years, or do they change?
They add so for the last 3 years they've been monotonically growing. I mean, they've included the previous year. The fact that our score was identical between the 2 years makes me believe that it's not getting easier or harder. It's the same. It's just a larger data set. Okay, now, so I guess what I'm going to talk about now is sort of methodology and various things we've tried, and the grammar formalism that we've used as a generalization of our model. So in this process of graduate student descent, I think it's important to mention things that don't work, as well as things that didn't work for us, I should say, as well as things that did work for us. So there are obvious things that one would like to do, like deeper models. So you'd like to take the face part, say in this model, you'd like to take that face part and make it deeper, give it eyes, nose, mouth, and so on. So we've tried, it turns out that if you take the places that the detector is finding a face, and you take the high scoring places where it's finding a face, and you just pretend that those are annotated boxes, and train a model on the faces. You can train a deeper model. You get a beautiful looking model. Another thing I learned from working on this is that when you look at a model and say, God, that looks beautiful, it doesn't mean anything. This looks like a beautiful face model, but we couldn't improve our score. And I don't really know why. That's another thing that happens in machine learning. The machine learning algorithm does something, you get some score, and sometimes it's really hard to know what's going on, or to be confident. You can have an intuition. Okay, the next thing I'm going to talk about is object detection grammars. So it's clear that I had that and/or graph in the beginning. And that deeper face model was an attempt to extend the and/or graph deeper to have a deeper layer of structures. Obviously, parts are recursively objects that can have parts. We can have the subcategorization of person into different kinds of people can be thought of as different productions from a root grammar non-terminal for person. So I'm just going to skip this and skip to the formal model. So we actually have a formal object detection grammar model. The code is actually written in a way that takes a visual grammar as input. So we can actually write visual grammars as a modeling tool, input the grammar structure to the code, and have it train filters for that grammar structure. So the grammar model has productions. This is kind of a speech and natural language place. So how many people have seen stochastic, probabilistic context-free grammars? So we have a weighted production. This is a non-terminal like person. Person might go to head, different parts of the person. There's a set of non-terminals. We'll let Y range over a union of non-terminals and terminals. Alpha is just a real weight. Modeling placement. So these are visual grammars. They're not string grammars. Question?
So in NLP, like when you have that grammar, you go left to right. But how do you define left to right there?
So
you have 2D done, right? Like you can go left to right.
Yeah. So this I put curly braces around this. This is a bag. So it has no order. So it's just a bag. So non-terminal goes to bag of non-terminals. But what we're actually going to do is have this notion of a placed non-terminal. So the non-terminal. So we have these filters, or in general non-terminals. A placement in our setting is a position and size. I didn't mention this, but we actually search. We're not just scanning over positions, but we're trying all sizes. Right? We're going through this size space. Yeah.
Is there a natural interpretation of these non-terminals? And did you start with, and did you have a collection of images that were labeled this way?
So the grammars that are working for us are very shallow. So there's a person non-terminal. There are the three different that has three productions for three different kinds of people. Each of those person models, each of the three has productions that generate the parts. And then the parts have productions that generate the placements of those parts. So it's a three-level, very simple three-level non-recursive grammar. The idea is that even from just bounding box detections, you could, in principle, write deeper, more sophisticated grammars and train the parameters of those grammars even from the weak bounding box labels. So I'll get to that, but an important point there is that although we are in fact using a grammar model. It's a simple one, but it's a grammar model. And the parse tree is not annotated in the training data. Okay, so what that means is that our inference algorithm is inferring a parse tree that's not annotated, but it still is training data. It has the bounding box. So we're training the grammar model just from the bounding box annotation. So the way we think about this is that this little omega is a specification of a position and size. This says at a certain place at a certain size. So this says y at place and size omega. So then our productions, the real productions we use to say that x at place omega, place and size omega, goes to this bag of non-terminals, each of which is at a place and size, which is a function of omega. So this, I should say, not all of our productions have this form. This is a, so think of one of the people model. This is a person at place and size omega. It expects to see a head at place and size f1 of omega, which is the nominal position of the head, and so on for the other parts. So this is the nominal position of the head relative to the position of the person. Okay, now we take this guy, the head, so we're looking for a head at a certain place and size, but that can go to looking for a more firmly placed head at some other position where there's a quadratic cost for the deformation. So this is looking for a head at this place, but I can find it at some other place with a quadratic cost for the deformation. Yep. Mitch.
The bag, the position of these guys are independent of each other's position. The position is dependent upon the head of this construction.
Yes.
But they're free to float.
Right. So this is a context-free grammar in that sense. And that's what makes dynamic programming. I haven't talked about the dynamic programming algorithm, but we're going to do dynamic programming to efficiently find the parse. And it's that independence, so the non-terminals are independent given the head, allows the dynamic programming.
So David, just to clarify some more, so if X, for example, were a car,
right,
and Y1, Y2 might be, front wheel, back wheel, door, but then the F, they're connected to the X, right? Meaning if I'm to place a car of this size at this point in the image, then I expect the front wheel to be over here, the back wheel to be over there.
Right.
So that's then the notion of, because Arya was asking earlier, are these Ys ordered in some way? And they are spatially ordered by the F.
They're placed. I like the word placed. Right.
So they're placed by the F.
Right. There's no first part, second part, but each part is placed.
A part over there and a part over there and a part over there.
Right.
And then it's not like, unlike a string, that's exactly where it has to occur. That's just a nominal placement.
That's a nominal placement.
And
That's
the
right.
detector will look in some neighborhood, and wherever it finds its best fit,
Right.
it will then take the difference, and that will be added.
Right. And the deformations are independent. Then the deformations become independent, which allows the dynamic programming.
So in particular, it's possible then that if I expect a person of a certain size, then when I look for their left and right hands, I might find different sized hands.
Our model doesn't do that. You could. We can type in a model that has that, but because we allow this to change the size, or we could allow the deformation to change the size.
Yeah, that's what I meant. The deformation will allow the size to change. So
Deva Ramanan, and then you can do dynamic programming over a search for the part over both size and place. And Deva Ramanan at UC Irvine worked hard on that without I think he got almost no improvement. One of those things that you'd think helped. Okay. But I didn't talk about the terminals. So here's the grammar. Eventually, these go down to terminals. Like this y prime, in our model, this y prime becomes a terminal, is a terminal symbol. When you reach a terminal symbol, there's a filter. These slides are written to be abstract. So if you go back here, there's nothing in this slide that says we're doing vision in either of these slides. Right? The placements, we can have a grammar with a placement space, and we don't have to be doing vision. It's a completely general setting. So to follow the general setting, for each terminal symbol A, there's a function that takes its placement and an input. So in vision, this would be the placement in the normal sense of position and size. This would be the image, and it returns a real score. So for every terminal symbol, placed terminal symbol, we get a score from the image. And that score from the image, let me go back up here, is the score from the image is just, you take this filter, you lay it on the image, and you get a score, whether, depending on whether these edges in the filter match edges in the image. And there's a large number of papers that have been written on that, on the precise details of that feature set that I'm not going to go into. Okay. Now I'm going to start talking about how this fits in with a support vector machine. So how do we view this grammar, sophisticated grammar training algorithm as a kind of support vector machine? So a support vector machine is a linear classifier. It maps an input, it takes an input, maps it to a feature vector, takes a linear weighting of the features to get the score. So we're going to do, turns out that we can do that for this whole grammar setting. And the way we do that is for each production of the grammar, we can associate the production with a feature vector. So there might be a feature saying corresponding to the weight of this production. I could have just this can be a sparse feature vector that has many different features in it, one of which is just 1 on for using this production. If you have a terminal symbol, a more interesting feature is just to say that if I have a terminal symbol and an image, now I'm using I for image, and a placement, there's the image edges at that placement of the terminal symbol. And I can extract those edges as a big feature vector, a big image, a feature vector. So now, if I have a complete parse tree, I can take that parse tree and compute one big feature vector by adding up the feature vectors at the terminals, which are little edge images, adding those all together from all the terminals, together with features saying what productions I used, and there'd be features representing deformation costs. And the point is you can take the whole parse tree and extract a feature vector. And then the score of the parse tree is just the inner product of the feature vector and the weight vector. Okay, and that lets us use an extremely general notion of latent support vector machine, or LSVM. This is also called a multiple instance SVM. Thomas Hoffman developed the concept independently, and we were unaware of that. But this is a support vector machine. So if you know SVMs, you might recognize this equation. This is the hinge loss. And SVM says you set the parameter vector of your model. So this is going to be our learning algorithm. The learning algorithm is going to set the parameter vector of the model to be something that optimizes, that minimizes a sum of a hinge loss and a regularizer. And an ordinary support vector machine has exactly this equation. This is the margin. So this is the max of 0 and 1 minus the margin. That's the hinge loss. The difference between this and a support vector machine is that the feature vector is a function of the input x, which is an image, and some other information, which in our case is the parse tree. Now the parse tree is not annotated in the training data. So this is where we come to the point where we're training from something that's not annotated. So that's why it's latent. There's a latent parse tree. So here, the latent SVM is a general SVM where the score on an input, so this is going to be treated as a binary classification problem. And I apologize, I'm glossing over. It's a bit of a cheat to map this to a binary classification problem, but at the level of the training algorithm, we mapped it to the problem of, is there a person near here or not? Right? So it's just a binary classification problem. The parse tree is still latent. You can think of it as, is there a person in the image or not? The score is a max over all parse trees, over all placements of the detector of the score of that detection. Okay, so you take the image, you take the max over all placements of the grammar of the score of that placement, treat that as the score of whether or not there's a person, and then apply this. Okay, now normally the hinge loss is convex in the weight vector. And the reason it's convex in the weight vector is that normally this is a linear term in the weight vector. And so you get a convex optimization problem in a support vector machine. Here, this max is a nonlinear operator. You get that this is convex in W, but here, whether this is convex in W is going to depend on the sign of Y. Because a max of convex functions, a max of linear functions is convex. So I don't want to spend too much time on this, but this is a semi-convex optimization problem. It's convex on the negative examples. It's convex when Y is negative. So it means you don't have to worry about the non-convexity in the background images. And if someone were to provide parse tree labels on the positive images, it becomes convex, even if they don't specify the parse trees on negative images. So this is just, so I said at the beginning that support vector machines have undergone an evolution in the last decade or so. This is, this is one slide on something called a structural, or a latent or hidden structural SVM. And Thorsten Joachim's, just in the last 2 or 3 years, published papers on this kind of SVM. I guess I don't want to go through this too much, but you can show that this training problem, so if you think of machine translation, you're taking an input, which is a sentence, and you're producing an output, which is a sentence. What that means is it's not a binary classification problem. It's a kind of decoding problem, right? You're taking a structured input and you're decoding it into some other kind of structured object. So is there a notion of SVM that's appropriate for training decoders, things that are producing complicated outputs? So this structural SVM, a structural SVM is a decoder. So Y here is the decode. And so this is a generalization of hinge loss. It turns out that you can show that if you're decoding to a binary classifier, this becomes the classical hinge loss. But it generalizes to the case where Y is an arbitrary decoding. You're assuming you have a loss function between the true decoding and the one you're trying to generate. And this is a margin between two scores, the score of the true decoding and the score of the one you're trying to generate. So I don't want to go into details, but I want to point out that support vector machines have undergone this evolution. And this concept also handles latent information. So I should have pointed out that down here, the score is still a max over latent information. So this is a latent structural support vector machine. So the decoding might involve a parse tree. Like if a translation system builds a parse tree, the parse tree is not in the annotated training data. And you can still deal with it this way. Okay, so I've already explained semi-convexity. You may be familiar with the concept of a conditional random field. So a support vector machine is based on hinge loss. A conditional random field is the case of a structured translation based on log loss, where the loss is 1 over the probability of the output given the input. That's also undergone evolution, the notion of a hidden conditional random field. Okay, let's back up a minute, be a little bit less technical. This is something we discovered. It's a sort of a fun slide that I have no explanation for. Pedro, for some reasons that I still don't really understand, suggested that we modify our training equation so the training equation before was an argument over W of a hinge loss plus the norm of W squared. Okay, so Pedro said, for some reason, let's not just take the norm of W squared. Now, our model has the final model has 3 different models of people. So we have parameters for the first model, parameters for the second model, parameters for the third model. The overall model, the norm squared, the weight, complexity of the overall model, in the traditional SVM, is the sum of the complexity of the 3 parts. Right? Is the norm squared of the first part plus the norm squared of the second part plus the norm squared of the third part. Pedro said, well, let's not do that. Let's take the max over the 3 components of the complexity of the max. For some reason, it worked. And to this day, I don't really understand why this. I called it voodoo regularization, or regularization voodoo. More recently, we found that it doesn't make that much of a difference. But it's another thing that we encountered. Part under training. This is another. I'm going to skip this because we're getting close to the end. Okay, the last thing we tried to do, and when I first gave this talk, I gave it at Snowbird, and Jan LeCun was there, and the whole community there was into neural networks. And it turns out that you can take this grammar model and reformulate it in a way that makes it almost equivalent to a convolutional neural network. And I really thought that making things nonlinear in the way that convolutional neural networks do would help. So the way you turn this into a convolutional neural net. So first, let's review the way the ordinary linear model works. Right? If I want to know the score, what I'm going to do is I'm going to take the linear model, which is this equation, explain this equation, then modify it to get a neural network model. Okay, so we take this first model, and this is the score of a non-terminal x at placement W in image I. Okay, so what I do is I look at all productions from x at that placement, and there's a certain feature vector associated with that production. I take the score due to beta now is the parameter vector. I was calling it W before. I take the score due to using the production plus the sum over these guys of the score of those guys. Right? So to compute this guy's score, I take the max over productions of the score I get from that production. The score I get from that production is the sum of the score I get from using the production plus recursively the score of the parts. Okay, and finally I get down to leaves. Okay, let's make it a neural version. The neural version says the score of this non-terminal at this placement is a max over productions, same as before, of a sigmoid, a nonlinear sigmoid function that's bounded, of a sum of this score plus a linear combination of the recursive calls. Right? So this is think of this as a unit. As the neural net people would call it a unit. Right? It's a placed non-terminal. It's going to have a score. The score is going to be a max over expressions of this form, where these are recursively the scores of subunits. So I'm taking a linear combination of subunits, passing it through a sigmoid to get the cost of a production, and then I'm taking a max over that. So this is a max sum alternating neural network, which the neural people, Tommy Poggio has been into alternating max sum neural networks. So I was convinced we would get mileage out of this because we've got this nonlinearity. So You can think of this as a log probability. But we could not get this to work. And one problem is, how do we train? We don't have a good way of training these weights alpha. We end up being nonlinear in these weights because they're getting multiplied down the network. So we could not get this to work. I'm going to skip this. The bottom line is, one of the other things we did was imposed a coarse-to-fine methodology. So we look at an image, we use a cheap detector to find a subset of the images where the head might be, a subset of the image where the, for each part, we find a subset of the image based on a cheap detector that we're going to restrict our attention to for the more expensive model. That's the cascade model. We got about an order of magnitude improvement in runtime by pre-filtering the placements with a simple model. All right, one last thing, and then I'm done. We've got this detector where we can type in an arbitrary grammar and train it. And Pedro believed, and I believed, it made sense, that this would be a very powerful tool. We would be able to type in sophisticated grammar models, say of people, and by using knowledge of people, and then by training the filters, we would get powerful detectors. And I kept saying, well, why don't we just type in? So one of the things that the detector does is, when it's trained over 20 classes, each class uses exactly the same training algorithm as each other class. There's nothing in the learning algorithm that knows about people or cars or bicycles. It's a completely uniform learning algorithm. So I thought, why don't we just type in a grammar just for person? You know, we could make an articulated chain grammar for the, articulated chains fit really well into the grammar formalism. We could make an articulated chain grammar for arms. One thing that I didn't mention, you might have noticed, is that the automated learning algorithm completely gives up on arms. They're too deformable for people. But why can't we just type in a grammar that is our knowledge of person, and we should do better? So we kept trying to do that, and we kept not doing as well as the general learning algorithm until we did this grammar. This was really, we gradually realized that the score the score for the person category in Pascal is largely determined by getting the bounding box right. We were getting lots of, there's a 50% overlap rule, which I failed to mention. Your bounding box has to have intersection over union of 50%. We would have correct detections. The detector found the face. But now, what's my bounding box, right? My bounding box stops here. Can you tell that that this is a lectern blocking me rather than my legs, right? If I walk over here, the bounding box is completely different. Can you tell that the person's sitting at a table? So it's all, the score in person in Pascal is all about getting the bottom boundary, the bottom occlusion boundary right. And so we eventually, Pedro and Ross, typed in this grammar. This grammar generates this thing first, and then it starts generating more parts. It's a grammar, so it can say, this can go to a production that generates this can go to a production that generates this. At any point, it can stop and output this guy, which is called the occluder. Right? So it generates some prefix of this and then outputs the occluder. That's what the grammar does. And we got a 2% boost in person with this occluder grammar over the generic person grammar.
Did it mainly just help with the bounding box, or did it find persons that were missing earlier because you were trying to find other parts that didn't exist?
It's a little bit hard to tell because we don't have good annotations and automated tools. Okay. And that's a real statistical question, and we're only looking at a 2%. It appears, looking at examples, that it was about occlusion, that it was getting the occlusion boundary right. So I'll stop there. The top level point is that we're trying, and still trying, to move, so to speak, back up the Chomsky hierarchy, integrate machine learning with more sophisticated models, and hopefully these ideas will extend across many domains, just like many of the ideas in machine learning are intended to be cross-domain ideas. So I'll stop there and take questions.
the tasks, in particular like natural language parsing and grammar induction. Do you have any sense for why I'm thinking about the SVM method of training the grammar on a corpus. Why it would or why it wouldn't work well with the natural language grammar?
So I think the basic methodology, so I have issues with the SVM framework that I haven't talked about. In finite dimension, SVMs are not consistent. They don't necessarily produce the weight vector of minimal loss. So we've had a series of papers with Joseph Keshet and Tamir Hassan on non-convex but consistent training algorithms. And there's a paper at NIPS last year on something called direct loss. And in the machine translation community, there's been considerable work on perceptron update. Several papers on perceptron update rules that look at n-best lists and try to move from those that are better by the blue, from those that are worse by blue score to those that are better by the blue score among an n-best list. And so, in terms of the SVM formalism, I guess in the setting of natural language, I'd say this direct loss idea has already proven to be effective in that domain, and there's good theoretical reasons to believe that that's perhaps a more effective cross-domain training algorithm.
So I've got a question. So in natural language parsing, supervised machine learning always outperforms our unsupervised methods. And here, where you draw the analogies between grammars and images, it seems like there's always an unsupervised setting. Could you imagine what a supervised grammar for image would look like? And do you imagine that would do better than your latent or unsupervised models?
So I can imagine annotating, Shinder Malik at Berkeley has, in fact, gone and annotated all the the Pascal data with so-called key point locations. So top of head, shoulders, elbows. And you can think of that as being annotations that basically specify the positions of the parts, so to speak. It's surprising, but in vision, those annotations have not led to big. You'd think that those annotations would lead to big boosts, but
I guess it might also be in nature of what you're being evaluated on. So in parsing, you would be evaluated on bracketing or something like this. And here it's more coarse in that you only need a bounding box around the object, so you don't need to identify.
there's a whole other set of data sets on pose estimation. This data set, I think there's a data set of lectures, Buffy the Vampire, that they've gone and labeled elbows and so on. And there, the task is not just to draw the bounding box, but to find the elbows. And so by that measure, the annotations are important.
I kind of want to follow up on my question and also turn it around a little bit. So I think one thing that is different about your situation versus unsupervised grammar learning, as it is often done in NLP, is that in NLP, we're also sort of trying to learn the topology of the model, where you're basically given, as I understand your algorithm, you're sort of handwriting these grammars and then you're learning the parameters. Is that roughly right?
I just want to modify that.
Okay.
In the 20 categories, we're using the same grammar across all 20.
The what?
For in Pascal, there are 20 categories.
Right.
And we type in the same grammar for all 20 categories.
Same grammar for all 20 categories.
Just different weights.
Just different weights. Right?
Oh, it'd be helpful actually to know what that grammar is. Did you have it on a slide? Presumably something where you have some.
It's just the top level category goes to 3 other non-terminals saying which model you're using.
Right.
Each one of those goes to a bag of parts. Each part goes to a deformation. And then you're down to the ground filters.
But I guess what I want to be clear on is that grammar is entirely handwritten. Is that right?
Well, it is handwritten, but it's it's what I just said.
It's what?
It's just a template.
Okay. What I I guess what I'm wondering is, if you wanted to scale this in a different direction, so you wanted to recognize thousands of types of op-eds, is the bottleneck actually writing that template?
So this system could easily be applied to, I mean, let's say instead of saying I want to do thousands simultaneously, I pick one. Somebody wrote a list of thousands, I pick one at random and annotated some data and trained. I would probably do pretty well on that object.
Okay.
But now if I've got 1,000 labels and I have to say which one, there's going to be a lot of confusion. And there has been work on trying to put the categories into trees and sharing models. You know, models get more refined as you come down the tree. And the score at a leaf incorporates scores up the tree. And Antonio Giralda and people at MIT.
Can you talk a little bit more about the deformation?
So this is a placement, right? Position and size.
Right.
And this says that if I'm looking for a head at this nominal position and size, I can find it somewhere else. So this is really a schema for all the different deltas I might put in here. And it's going to, the cost is going to be quadratic in the size of the movement from the nominal position to where I actually find it.
But how about the size?
So that was Sanjeev's question. So in principle, you could be deforming it both in position and in size. But in our model, we just deform it in position. We don't look for it at a different size. But you could search over sizes as well.
The nominal sizes are, you just assume that you have them?
So the resolution of the filter is always taken to be a factor of 2 finer than the resolution of the filter. So the resolution of a part filter is always taken to be a factor of 2 finer than the resolution of the whole object filter. And that's just fixed. That's just a factor.
Do you check for like a set number of displacements then? Like you have like 1 pixel out.
So the score of this is going to be a max over productions.
Right.
So
Is there a finite number?
So the image gets divided into cells. These filters have these little edge. Each one of these filters is divided into little cells, and each cell has a histogram over edges. And we do step 1 cell.
So that delta would range over a set of, it would scan this box.
Over an integer number of cells. So I could move that 1 cell to the left, 2 cells to the left.
My question probably goes back to what Chris was asking you about supervised. If you just go back to this slide. So I'm thinking that the way you train things, if I understood right, is that when you're training a object model X, right, then you say that X consists of parts y1 through yn, and the nominal locations are also learned, I suppose, right? That's part of the parse tree and so on. And in your training, you have no parse trees. So the F's are
in the training data.
Yeah. And so in some sense, you're hoping that y1 will be the, like, if for a car, it would be a wheel or a door or a body or something and so on. But in reality, you have no control over it, right? It will learn what it learns, right? And when you said that when somebody segmented the parts of an object, it didn't make a lot of difference to the learning. One reason could be, and this is related to some other experience we have with speech, that the total contribution to the likelihood of the energy function because of these F's and the deformations is so small compared to the contribution from the underlying filters at the bottom, that in some sense the filters lock on to the visually most prominent parts, and that becomes a y1 through yn. And it's almost not necessary to figure out the supervised location functions Fi's, because their contribution is so small, you might as well have it wrong. It doesn't matter. This is just speculation, but for example, when we train an acoustic HMM, we can throw away all the transition probabilities and not even compute them. And it makes no difference to our recognition.
I think there's an element of truth in what you're saying. That deformation costs end up being a small fraction of the score.
Right.
Yeah.
They might, however, still be useful in guiding search. So even if even if they weren't so helpful in comparing trees that were given, it might be nice to know that once you found the right hand over here, you might look for the left hand over here and not bother looking at other locations.
In fact, we limit the. This could, in principle, look over the whole image. Could allow this to be over the whole image, but we in fact found that to a feasible set that's of reasonable size deformations. So we don't look for a person's head who's small on the other side of the image. That makes sense. Yeah.
So I want to persist on the linguistic analogy thread a little bit. And I think I probably asked you at least one of these, about at least one of these two analogies in MLP, but I'll ask again. There are two things that might be interesting to do with rule of the form you have at the top here, x goes to y1 through yn. And one is to try to learn probabilities of variance of the same rule, which would be like lexical redundancy rules in a lexicalized grammar, or different subcategorization frames for the same verb. So it might be that sometimes x consists of n parts, but sometimes it consists of only n minus one of them. Some of these parts might also be iterated. So a car has four wheels, but there might be a Christmas tree. The more ornaments you have, the more of a Christmas tree you are. So there's one question is the variation in the rules. The other question is about slash categories, which might be a way of handling occlusion. So you've learned this special category of an included person. But if you were trying to get a parse of the entire scene, you would like to actually find the lectern and say you would like the upper half of a person to be able to fit exactly together with the lectern that is responsible for the pixels below him.
So I would agree. I don't know how useful it is to think of it as a slash category in a technical sense, but I would agree that we really would like to go to whole scene interpretation, to interpret every part of the image in some way, maybe just ground, background. But it feels reasonable to me that you're able to easily see that I'm blocked by this because you recognize this.
And the difficulty is when you're trying to parse the whole thing, making sure that every non-transparent pixel is explained exactly once. That's
a combinatorial problem, right?
It's a combinatorial problem, right? So Greg Hager and I a couple of years ago were talking about grammars much like this. I mean, a number of details were different, but we kept sort of coming back to this notion that you wanted to use, you wanted to be able to model occlusion directly in the generative process. And maybe the search process would do a course pass that didn't deal with occlusion, but you would know, you could then reevaluate if you think of some kind of re-ranking model or something under a regimen where you really were trying to explain every pixel once. And so slash categories were a nice notion for this, but the problem is it's not just, if you've got a left slash and a right slash, that's easy in text because it's linear. But here you want to take a bite of some irregular form out of the bottom of somebody because they're being blocked by a small dog, large dog, whatever.
Right. No, I would agree with that. One thing that I sort of do think one sort of has to do is I talked about this graduate student descent and the Moore's law and pursuing the metrics and it's. There are lots of ideas that make a lot of sense, and the hard part is translating that into a boost by some. It doesn't have to be this metric, but I do believe strongly in keeping your nose sticking your nose to the metric.
One promise of this, or for that matter, what you're doing with the parts here, if you could build in a model that said X consists of these parts, and this is the likelihood with which this part might be missing, then in fact, you'd go one level further. You could say, here is a one-armed person, not just one person. If you wanted to do whole scene interpretation, there was another project we had over the summer where we were trying to figure out how people describe images. and when people describe them, they often point out the irregularities. They might say it's duck without a beak instead of just a duck. Whereas if it had a beak, they wouldn't say it's a duck with a beak, because that's always that beak.
I guess there's one more thing I wanted to say about the part annotations. And that is that, like, I don't know, look at these edges right here. You wouldn't necessarily think of that as being important, as being an important part, like sort of the side of my body. And one thing that the machine learning can do is find discriminative things that you didn't expect. So the parts that you think are discriminative might not be the ones that are actually discriminative. Liu Zhu we have a complicated algorithm for finding initial part placements in the model. Finding initial nominal positions for all the parts, and covering the root filter. We have a complicated algorithm. Liu Zhu just built a grid. Just took a grid, built a grid, and allowed the grid to deform, more like a diffeomorphism model. And it did just as well, if not better. So it's not even clear that the use of the word part is appropriate as opposed to just deformable edge template.
Let's thank the speaker once again.